Hi, hi to everybody. In this lecture video, we're going to be doing chapter 36, and chapter 36 is about the image formation. Now, after doing this chapter, you'll be able to know the formation of image and properties of image formed by plane and spherical mirrors, and you'll also be able to derive and apply the mirror equation, and you'll also be able to derive and apply an equation for images formed by refraction of light by double interference, and you'll also be able to derive and apply thin lens formula and the lens maker's equation, and you'll also be able to know image formation by lenses using algebraic and graphical methods, and you'll also be able to know what the lens aberration are, and you'll also be able to know what angular magnification is, and you'll also be able to know the image formation and magnification of a single magnifier or microscope and a telescope. And of course, you'll also be able to apply the above and solve the problems on the above concept. Now, let us just start with the notation for mirrors and lenses. Now, the object distance is the distance from the object to the mirror or to the lens, and that is denoted by small p, is denoted by alphabet small p. Right. Now the image distance is the distance from the image to the mirror or lens, and it is denoted by this q, by the alphabet q. Right. Now the lateral magnification of the mirror or lens is the ratio of the image height to the object height, and that is denoted by the alphabet capital M. Right. Now, in terms of the images are always located by extending diverging rays back to a point at which they intersect. Images are located either at a point from which the rays of light actually diverge, or at a point from which they appear to diverge. Now, there are types of images. For an example, there's a real and a visual image. Now, a real image is formed when the ray passes through and diverges from the image point. Real image can be displayed on a screen. Now, a visual image, on the other hand, is formed when light rays do not pass through the image point but only appear to diverge from that point. Now, visual images cannot be displayed on the screen. Right. Now, the image formed by a flat mirror, for an example. This is just the simplest possible mirror. Now, suppose that you have your object here at this point. Now, the distance from the object to the mirror is what we denote by this small p, and the distance from the mirror to the image is what is being denoted by this small q. Now, in this case, the rays leaves the source, and they are refracted from the mirror to the human eye. Now, the point I is called the image of the object at O, at point O. The object at point O. This I is just the image of this object O. Now, the image is visual because it is actually on the other side of the mirror. It is not in the same side as the object. You will see later on when we talk about the real image and the visual image. Now, a flat mirror always produces a visual image, which means the image is on the other side of the mirror. Now, the geometry can be used to determine the properties of the image. There are an infinite number of choices of direction in which light rays could leave each point on the object. Two rays are needed to determine where an image is formed. Now, for an example, as I have already said, now only two rays are actually needed. The first ray is that ray which goes direct to the mirror, which is moving parallel to this axis, and the other ray that is required is that ray which moves from the top of the image to this center of the mirror, and then it reflects back to this side. Now, in this case, another ray allows the path PR, the path PR, which is nothing else but this one. Now, the triangle PQR and P prime, Q, R are the congruent triangles. Now, in this case, because the triangles PQR and PQR are congruent triangles, therefore it will mean that the magnitude of this distance from the object to the mirror, it must be the same as the magnitude of the distance from the mirror to the image. Now, as a result, because of that, therefore that will mean the h, which is the height of the object, must be the same as the height of the image. And this is only applicable only for the flat mirrors. You will see later on when we deal with the other types of mirrors. Right, to observe the image, the observer will trace back the two reflected rays to point P prime. Point P prime is the point where the rays appear to have originated. Now, the image formed by an object placed in front of a flat mirror is as far as behind the mirror as the object is in front of the mirror, which means the distance that your image, when you are looking at yourself in your image, the distance from yourself to the image is the same distance from the mirror to your image on the other side of the mirror. As a result, as I've said, the magnitude of P, the object distances, must be the same as the magnitude of the distance of the image. Right. Now let me also say something about the lateral magnification. Now the lateral magnification, which is actually denoted by the capital M, is defined as the image height, the ratio of the image height to the object height. And as you have seen, that the image height is denoted by small h prime, whereas the object height is denoted by this small h. Now, this is a general magnification for any type of mirrors. It is also valid for images formed by the lenses, as you will see later on. Magnification, by the way, does not always mean bigger. The size can either increase or decrease. I just want to read it again. Magnification does not always mean bigger, because the size can either increase or decrease. Now, M can be less than 1 or it can be greater than 1. For an example, in the case of the flat mirrors, we have seen that the height of the object is the same as the height of the object. Therefore, this is just going to be 1. But there are some instances where this can be less or greater than 1, as you will see later on when we deal with other type of mirrors. Now, the lateral magnification of a flat mirror, the lateral magnification of a flat mirror is just +1. This means that h is the h prime, the object height is equal to the object the image height for all images. The positive sign indicates that the object is upright, which means the object is just upright, is pointing at the same direction as the image. Now, some orientation that is the same orientation as the object, right? Now, the reversal in a flat mirror, I just want you to be aware that when you put your right hand in your mirror, when you look at your right hand in your mirror, you place your hand like this, and that right hand is nothing else but it reflects your left hand. Now, I just want you to do that experiment so that you can be able to see what I am actually talking about. I mean, the same thing happens with your eye. Your right eye in the image is your left eye. So please just do that 1 second or 2-second experiment to get things all right. Right, now the reversal is actually a front-back reversal. It is caused by the light ray going forward towards the mirror and then reflecting back from it. Right, now the image as far behind the mirror as an object is in front, and that is the magnitude of the object is the same as the magnitude of the image, as I've already explained for the flat mirrors. Now the image is unmagnified. The image height is the same as the object height. Therefore, the lateral magnification, the capital M, is just a +1. Now the image is therefore visual. The image is also upright. It's pointing at the same direction as the object. It has the same orientation as the object. That means when we say the image is upright, it's not inverted. Now there is a front back reversal in the image. What I also want you to do, I have a spoon here. This is my spoon. And in this case of the spoon, what experiment that I want you to do is I want you to look at your image. Look at your image in the spoon, at the concave side of the spoon, at the concave side of the spoon. And you look at your image, and I want you to turn the spoon and look at your image at the convex part of the spoon. And then you tell me what are you seeing. Now in this case, when I'm looking at the convex part, the image is upright, is pointing at the same orientation. But when I'm looking at the concave part, the image is actually inverted. It is upside down. So that's what I am trying to build in you as far as this is concerned. But when we are talking about the flat mirrors, the image is always upright, right? That is the same orientation as the object. Now let us just do the following quick quiz. You are standing approximately 2 meters away from a mirror. The mirror has a water spot on its surface. True or false? It is possible for you to see the water spot and your image both in focus at the same time. No, that cannot be true, because remember, if you are standing 2 meters away from the mirror, which means your image is actually 4 meters away from you, and the water droplet is actually 2 meters. Therefore, it is false. You cannot be able to focus at the two at the same time. Right, now let us also do the following conceptual example 36.1. Now, multiple images formed by two mirrors. Two flat mirrors are perpendicular to each other, as in the figure, and an object is placed at point O. In this situation, multiple images are formed. Locate the position of these images. Now, in that case, you are just going to have, I mean, if your eye is situated in this position here, now the first image that you are going to see is I1, and that is just due to the light the light ray moving from the source, from the object, and then reflected back to your eye. That is just going to be the position of the first image. Now the second image will be from this point to that point, because this object will reflect to this mirror 2, and then the rays will just be as if the rays were moving from the object in this way. Now the object will just be, the rays will be moving in that mirror, and then they will be reflected back to your eyes. And now the last image is just going to be this reflected light from this object to this mirror, to mirror number 2, and then from there they reflect back to your eyes. Now when you look at this visual image, it is as if the light was coming from this object. Now you are only going to have three different images that you are going to see if the mirrors are placed in this fashion, which is perpendicular to each other. And of course, if your eye is situated at this position, right? Now, the application of all these things is for example, the day and the night setting on your auto mirrors on some of the cars. For example, the day setting is actually shown in this figure A, while the night setting is shown in figure D. Now, with the day setting, the bright beam B, which is this bright beam B of a reflected light, is directed into the driver's eye. This light for beam B is actually reflected to the driver's eye. Whereas with the night setting, the beam D of reflected light is directed into the driver's eye, while the bright beam goes somewhere else, which means the bright beam is actually not coming to the driver's eye. That is, during the day, the automatic mirrors will just adjust themselves accordingly, so that those two types of this, the bright and the dim beams of the rays of light are actually going into the driver's eye, and the other one is not going, and it just depends on the day setting or the night setting. So automatic cars can just adjust the mirrors accordingly. Right, now let me also move away from the flat mirrors and then introduce you to the spherical mirrors. Now, a spherical mirror has the shape of a section of a sphere. The mirror focuses incoming parallel rays to a point. Now, a concave spherical mirror has the silvered surface of the mirror on the inner or concave side of the curve. That is the concave. I'm just going to make a good example of a spoon. So the concave mirror would just be this mirror of this shape. So the silvered part is this part of the mirror. Now, the convex spherical mirrors has the silvered surface of the mirror on the outer of the convex side of the curve. Now, the concave mirror is this mirror of this type. Now, you can either have the concave and then you can either have the convex mirrors. And in some instances later on, you will see that you can also have the combination of both type of mirrors. Now, where will be the image? So this is where we are actually going to study from now onwards, because for the concave and the convex the situation is going to be different. For an example, when you take that spoon and then you look at your convex part, the image is upright, but when you look at the concave part, the image is actually inverted, it's upside down. The image is actually upside down, right? Now in terms of the notation, the mirror has a radius of a curvature of say r. The curvature of radius is just r. This is the center of the curvature. And now this point C to V for the concave mirror, C to V is what you call the principal axis, and the point V is the center of the spherical segment. Now this part, the blue region of this represent the structural support for the silvered surface. Now this is your silver surface, the concave side, right? Now that's the notation that we are going to be using, where this C is nothing else but is the center of the curvature, right? Now let me also introduce you to paraxial rays. We use only rays that diverges from the object and make a small angle with the principal axis. Such rays are called the paraxial rays. All paraxial rays reflect through the image point. For an example, when you take this concave mirror and you have an object there, now the rays will just be going in this direction. Now all for the paraxial rays, all this object, this is going to be your image. They are just going to be reflected or they are just going to be reflected through the image point at I, right? Now the spherical aberration is when the rays that are far from the principal axis converges to other points on the principal axis. This produces a blended image. The effect is called a spherical aberration. Right. For an example, you see you have many points where these rays are converging, and they are sometimes converging not on the principal axis. Therefore, that leads to a blended image. As a result, those kind of aberration are what we call the spherical aberration. Right. Now, let me also talk about the image formed by a concave mirror. Now, when we consider the fact that when I have an object O at point O of a certain height h, now one ray will just be going direct to the center of the curvature, and then it will be reflected back in this fashion. Now one ray will just be moving through the center of the curvature through the concave mirror, and then it will just be reflected back. Now where will be the image? The image will be formed where these two rays are actually intersecting. Now the image will just be inverted image because it is just going to be upside down. Look at the direction of the object. The direction of the object is upward, but the direction of the image formed is actually downwards. So as a result, the image there is just going to be inverted image. Now I also want to emphasize that the distance from the object to the mirror is what we call the P, the small capital P, and the distance from the mirror to the image is what we call Q, and this distance from the center of the curvature to the mirror is what you call the radius of the curvature, because this is just a spherical I mean, if you have to do a spherical sphere around this because these are called the spherical images because they've got a certain radius which was supposed to be somewhere in here. If you have to plot a sphere along this, which will just join with this part of the sphere, right? Now in that case, the geometry can be used to determine the magnification of the image. Remember, the magnification is the ratio of the image height to the object height. Now in that case, h is a negative when the image is inverted with respect to the object. Now if I name all these angles as I've named them in these images, therefore I can be able to get the tangent of theta, and I can also be able to get the tangent of theta for this triangle, for this yellow shaded triangle, and I can also be able to get the tangent of theta for this red shaded triangle. Now if you do that, what are you going to have? The tan theta in that case of this triangle, the red shaded triangle, is just given by the opposite, divided by the adjacent. Now the adjacent is nothing else but it's just the distance from O, from the image to the center of the curvature. Now when I take the tangent of theta, for this yellow shaded triangle, this is what you are going to have. I'm just going to have h prime divided by q. But now, as you can see, that the tangent of theta is just the same as the tangent of theta. Therefore, what I'm going to have there, I'm just going to have h divided by p is nothing else but is the same as the h prime divided by q. Now if I have to take to get the magnification, which is nothing else but is just the ratio of that to the ratio of h. Now in that equation there, what I'm going to do, I'm just going to divide by h there, and then that q will go on the other side. Therefore this is just going to be nothing else but I will just switch this like that. I divide by h there, and then I take this q, I put it up there. Therefore this is just nothing else but it's just going to be q divided by p. So that's what you are going to have for your magnification, as I've shown you that we are just using the geometry to determine the magnification of an image. Therefore the magnification of the image is actually minus q divided by p. Why minus q? Because the height of the image is pointing at different orientation compared to the object itself, right? So that's why there is that minus on your equation. There must be minus in this equation here, right? So that's why you have that minus. Now h is negative when the image is inverted, because the object is facing up, and now the image is pointing at the negative y axis. Therefore that's why you have a minus sign for your lateral magnification, right? Now the image formed by a concave mirror, geometry also shows that the relationship between the image and object distance is gonna be written in terms of this, because I can also take the tangent of the alpha, the tangent of the alpha. Now if I take the tangent of the alpha, this is what you are going to have for the tangent of the alpha. Tangent of the alpha, I'm just going to have for alpha, this is what you are going to have here, the tangent of the alpha. Now this is just going to be the h prime, and then from here to there is nothing else but it's just going to be p, the r minus q, the r minus q. Therefore that is just going to be this, and the tangent of alpha can also be determined in terms of the h divided by p minus r, p minus r, the tangent of this angle, because these are vertical angles, while the angle of incident is the same as the angle of reflection for the previous case. So now if you do that, you can also show that the lateral magnification will just be the ratio of h divided the h prime divided by h. Now in that case, when you do that, this is what you are going to have in terms of your your lateral magnification. Now, if you rearrange this equation, this is what you are going to have, because we know that this h prime, the ratio of h prime to h is nothing else but it's just given as q divided by p, where this q is the image distance when this p is the object distance. Now, if you rearrange the equation, this is what you are going to have when you rearrange this equation. Just rearrange this equation. This is what you are going to have for the rearrangement of that equation. Now, this is what we call the mirror equation. That's the mirror equation. But let me also introduce you to the focal length. Now, this is the mirror equation that we have derived from taking the tangent of the alpha, because the tangent of the alpha for both different alphas, therefore you came to this equation here. Now, in that case, now if p goes to infinity, if this p goes to infinity, if p becomes very high, which means this number will just be very close to 0. Therefore, we can just say this 1 over p is just nothing else but it's just 0. Therefore, 1 over q will just be equals to 2 over r. Now, in that case, this implies that q is nothing else but it's just going to be r divided by 2. Now, when I want to call that r divided by 2 to be what we call the focal length, and is actually denoted by f. Where is the focal length of the mirror? It's actually this half radius. The half radius is what we call the focal length. Now, as a result, the mirror equation therefore can be written in terms of this equation, because I'm writing this in terms of the focal length. Now, if I'm writing this in terms of the focal length, it must be the inverse of that. Now, the inverse of that is just going to be this. Now, the mirror equation therefore becomes this. That is your mirror equation. Therefore, if you know the object, distance, and then you also know the image distance, therefore you can be able to determine what is the focal length of the lens. And of course, if you know the focal length and then you know the object distance, therefore you can also be able to get the object distance. And if you know the focal length and the image distance, you can also be able to tell what is the distance of the object. Right. Now, this is what we call the focal point of this the focal point of this concave mirror. Now, the distance from that focal point to the distance of the to the surface of the mirror is what you call the focal length. That is the focal length, right? And the focal length is nothing else but is r divided by 2, the radius of the curvature divided by 2, right? Now, the focal point, for example, when you send different lights on the concave mirror, for example, you can send a red, the green laser, the blue laser, and the red laser. When they are reflected back, they are going to via through your focal point, and that focal point is that spot where it's wide. Now, as you can remember that when you combine the red, the blue, and the green, you are just going to be forming a white light. Now, the focal point is where all the beams intersect, and it is the white spot in that point. Now, one good example of this concave mirrors is a good example is the satellite dish, which actually converges the microwaves to this receiver here. Now you start to understand why the satellite are being made like to be a concave of the concave shape, because when the microwave, remember, microwave is one of the the electromagnetic one of the electromagnetic spectra which falls in the electromagnetic waves. So they behave the same way the light behaves. So that's why this will divert or focus this microwaves to the receiver. Right. Now, let me also talk about the convex mirror. A convex mirror is sometimes called a diverging mirror. The light reflects from the outer or convex side of the surface. The ray from any point on object diverges after reflecting as through they were coming from some point behind the mirror. The image is visual because the reflected rays only appears to originate at the image point. The image is always visual because it is actually formed on the other side of the mirror. Right. Now, for an example, this is the image formed by the convex mirror. Now, in that case, when we apply the same rules, this the first ray will just go to that point, and then it will be reflected back, and there will be one ray which will just via through the center of the curvature. Now, in that case, you denote that by drawing the dotted line. Now, in that case, where these two lines meets, that's going to be your image. Now, in this case, you can see the object height is higher compared to the image height. Therefore, the magnification in this case is just going to be something else. It's not going to be the same as for the flat mirrors. Now, in general, the image formed by a convex mirror is upright, visual, and smaller than the object. So the object is visual because it is on the other side of the mirror. It is not on the same side as the object. Right. Therefore, it is visual, but it is upright. It is upright because it is actually facing on the same direction as the object. It is not happening like when you look at your concave side of your spoon. The image there is visual, but it is inverted because it is facing down. When you look at the concave on the convex part, the image is visual, but it is upright in terms of your spoon. I will really appreciate it if you can do that simple experiment. Right. Now, the sign convention for this type of mirrors, or this concave and convex mirrors. Now, when you are having a mirror here, even if you have a flat mirror, now the front side is, or the real side, things on this front side are real. The object is real. The image will also be real. But the back side of the mirror, things are visual there, or this is what you call the visual side. Now, the distance of the object to the mirror, P and Q, the distance of the image, are positive, but on the other side, on the back side, the P and Q are negative. Now, the incident light is coming on this side, and the reflected light is only on the other side. But on the visual side, there is no light. There is actually no light. Now, be sure to use proper sign choice when substituting values into the mirrors equation. And of course, this sign convention applies for the flat and the convex as well as the concave mirror. Right. Now, this is one of the tabulated sign convention. For an example, the object is positive when the object is in front of the mirror, but the object is negative when it's at the back of the mirror. And the object is visual when it is the back at the mirror, but it's really when it is on the front of the mirror. Now, the image is in front of the mirror, therefore the image is therefore real. But if the image is at the back of the mirror, therefore it is visual. It is the visual image. Now, the height, the image height is upright. Now, for the other one, if the image height is negative, the image is inverted, which means the image is facing at the upside down. Now, in that case, the focal length of the mirror is positive for the concave mirror. The image is the focal length. The focal length is positive. That F is positive for the concave, but F is negative for the convex mirror. Now, the magnification, the lateral magnification, the image is upright. Now, the image is actually inverted. Right. Now, let me also discuss in terms of the ray diagrams. Ray diagrams can be used to determine the position and the size of an image. They are graphically a construction which reveal the nature of the image. They can also be used to check the parameters calculated from the mirror equation and magnification equation. Right. Now, in this case, to draw a ray diagram, as we have seen in the previous diagrams, you need to know the following. The first thing that you need to know is the position of the object and the location of the focal point and the center of the curvature. Now, three rays are drawn. three rays are actually thrown. They all start from the same position on the object. The intersection of any two of the rays at the point locates the image. The intersection of any two of these rays locates the image. The third ray serves as a check of whether the construction is right or wrong. Now, let me first discuss these three different rays. Now, the first ray is thrown from the top of the object parallel to the principal axis and is reflected through the focal point, F. Now, ray 2 is thrown from the top of the object through the focal point and is reflected parallel to the principal axis. Now, ray 3 is thrown through the center of the curvature and is reflected back on itself. Now, it is thrown as if it is coming from the center of the curvature, which is P is actually, the distance is actually smaller than the object distance is smaller than the focal length of this mirror. Now, let me just show you, okay, I will also show you later this kind of rays that I'm referring to now. Now, a huge number of rays actually go in all directions from the object. Now, the three rays I am talking about, ray 1 and ray 2 and ray 3, were chosen for the ease of construction. The image point obtained by the ray diagrams must agree with the values of Q calculated from the mirror's equation, as well as the magnification. Right, for an example, this is the ray number 1 that I was talking about when I'm talking about the concave mirror. The ray number 1 will just be moving from the object, the top of the object. It goes direct to the surface of the mirror, and then it is reflected back through the focal point, of. Now, the ray 2, it's still moving from the top of the image, and then it is passing through the focal point, but it is reflected back parallel to the principal axis. Now, ray number 3 is actually moving through the center of the curvature, and then it is actually reflected back on itself. Now, where all these rays meet, this is where you are going to have your image. Now, in this case, the center of the curvature is between the object and the concave mirror surface. The image is real. Why the image is real? Because the image is being formed on the same side of the object. If the image was on the other side of the object, that image was going to be virtual. Now, in this case of the concave mirror, when the object is being placed there, therefore that is actually the real image, but the image is inverted. Which means the magnification is going to be negative for this inverted. Now, the image is smaller than the object, which means the object has been shrinked when we compare it to the image. Right. Now, let me also talk about when the distance, when the object distance is less than the f. Or before that, maybe I should just also show you in this diagram here. When I have a cangle here, and then I'm having the concave mirror there, do you see the image is actually inverted? But now this is only going to happen when I am placing the object very far away from the center of the curvature. When this object is being placed at the distance P is greater than C, the center of the curvature. Now, let me also put this object at the distance where P is less than the focal length of this image. Do you see now the image and the object and the image are facing upwards? But what is going to happen? Look at the image. Now, when I do the rays, the first ray will just be passing through the focal point. The first ray, starting from the head of the object, it goes and then it is reflected back when it reaches the surface via through the focal point. And now the ray number 2 is just going to be moving from the focal point through the head of the object, and then it is reflected parallel to the principal axis. And the ray number 3 is just going to be moving through the center of the curvature through the head of the object. As a result, when you construct this dotted line, this dotted line, it is as if the light was coming from this side of this image. Now when you look at the image, the object is between the mirror and the surface of the focal point. This is where it is. Now the image is visual. The image is visual because the image is on the back side of the mirror, and now the image is upright. The image is upright. Now the image is larger than the object. Now therefore, I am therefore concluding, and I leave it to you to throw this rays when this object is being placed between the C and F. Right. So this is what is going to happen. It depends where are you putting your object next to this concave or convex mirror. Now the rays diagram in the convex mirror. Now the same rays will just we just apply the same rays. You have ray 1 and up to ray 3. Now in that case, this is what is going to happen for the convex. Remember, for the convex, this is your object here. The convex is that kind of mirrors which are like this. These are convex, while the concave are this kind of mirrors. I'm just using that spoon once again. Now in that case, if you have an object, the first ray is going to go direct to the surface of your mirror, but now when it reaches there, it will be reflected back. Now when you do the dotted line, it is through the focal point of the convex. Remember, the focal length, or the focal length, is negative when you talk about the convex the convex mirrors. Now the ray number 2 is just going to be moving from the top of this, and then it will want to go through the focal length. It will want to go through the focal, but now when it reaches there, it is actually reflected back, and then when it's reflected back, it goes back like that. Now that's what you are going to have. Now for ray 3, it's just going to go through via the center of the curvature. Now where all these lines meet, this is what you are going to have your image. Now in this case, as you can see, the image is visual because it's on the other side of the image, but it is magnification is positive, it is upright, therefore the image is smaller, but the image is smaller than, because the height of that image, when you compare it to the object height, the image height is smaller compared to the object height. Now in fact, this is what is happening here. This is what is happening here when I'm taking my spoon. I want you to do that experiment. Now I'm looking at myself. My head is not as small as in this concave part of this spoon. So I think now you understand the reason why my head is smaller on the concave part of this spoon. So please, you just have to do this experiment in order to make it easier, and so that you can understand it even further. Right. Now, I also want to say something about the noise on these images. Now, in summary, with a concave mirror, the image may be either real or visual with the concave mirror. It just depends where are you putting your object. When the object is outside the focal point, the image is real. When the object is at the focal point, the image is far away. It is at infinity. When the object is between the mirror and the focal point, the image is visual. Now, with a convex mirror, the image is always visual and upright. It's always visual and upright. As the object distance increases, the visual image increases in size. Now, with this, I just want us to do the following quick quiz. The following quick quiz, I mean, if you wish to start fire by converting sunlight from a mirror onto some paper under a pile of wood, which will be the best choice for the type of mirror. Now I've also directed you, the best type will just be the concave mirror, and then I just want you to go to this link of the YouTube video so that you can see that the cardboard can also be bent by this concave mirror, because it will just focus this light to one spot, and the intensity of that light is just going to be immense and is going to be high. As a result, you can even bend the paper. And I think you have done that experiment when you were growing up, taking the concave mirror and then putting it, lighting the sun up until that spot is small. Below, underneath you put the paper. That paper will just bend. Now I've also directed you to this YouTube video so that you can see what is happening. Right. Now let us also do the following quick quiz. Consider the image in the mirror. in the figure, based on the appearance of this image, you will conclude that the mirror is concave. The mirror is concave, as you can see. The mirror there is concave. The mirror there is concave, and the image is visual. The image is upwards. Now, what I'm trying to say here, you are seeing these two scientists there, but there are other scientists, 4 scientists, which are, say, on the left side, and we cannot see them. So as a result, but we are seeing the image. That image is actually visual, because it's on the other side of the mirror. It's not on the real side. It's not on the front of the image. Is on the other side. So as a result, the answer for that quick quiz will be number B. Right. Now let me also do the following example 36.3, the image formed by a concave mirror. Now a spherical mirror has a focal length. You are given the focal length there. Locate and describe the image for an object distance of 25. Now you know the equation of the mirror equation. Now the mirror equation is given by this. Now you have to rearrange this equation in order to to find Q, which is the distance of the image from the surface of the mirror. Now you know everything. Now you just plug these things. Now when you plug all these things, this is what you are going to have. Now remember, because this is the concave mirror, the focal length is positive. Therefore, that's why you see 10.0. But if this was the convex, therefore the focal length was just going to be negative. Right. Now, as a result, the Q is just given by 16.7 centimeter. Right. Now, in that case, the magnification is the Q minus Q divided by P. As a result, this is minus 0.667. As you can see, the magnification can be lower than 1, because this is not a flat mirror. Now, as a result, we can see if the magnification is minus, therefore the image is inverted. Now, you can also be using the ray diagrams in order to test whether the image. Now, if you use the ray diagrams, they will always agree to these calculations. Right. Now, let me also do the part B, which is saying locate and describe the image for an object a distance at 5 centimeter. Now, when the object is placed at 5 centimeter, you can start using the rays, and as you can see with the ray diagrams, you can see that the image is actually visual, and that image is higher than the object height. Now, as a result, when you want to get Q, this is what you have to do. This is what you are going to have. Now, the Q is negative. The Q is negative because it's on the other side of the image. Now, this is what the ray diagram is actually telling us. That's why Q is negative. It's not positive compared to part A. Now, the magnification is going to be positive. The magnification is going to be positive because the image, therefore, is now visual because it's on the other side of the image. Now, let us also do the example 36.3, the image formed by a concave mirror. Suppose you set up the buckle and mirror apparatus as illustrated in the figure shown and described here in part A. While adjusting the apparatus, you accidentally pump the buckle and it begins to slide towards the mirror at the speed Vp. At the speed Vp. That speed Vp is nothing else but is the speed from the object distance. That's why it's a subscript P. Now, how fast does the image go to the buckle? Right. Now, in that case, we know what is Q. Q is given by this equation here. That is Q. We have to calculate the speed. But I just want to remind you something from your previous semester. You remember that the displacement is just given by S is equal to Vt. Now, this displacement S, in this case, when I want to get the velocity is nothing else, but the velocity can be given as the derivative of the displacement divided by the time derivative. So that is your speed or the velocity, right? In this case, you know what is Q. You know what is Q, and that Q is nothing else but that Q is, it can be this displacement. Therefore, for me to get the velocity, I will just have to take the time derivative of that Q. In that case, if I compare that to this, therefore the velocity, it will just be dq, the rate of change in this Q, in this position of the image. So that's what you are going to be doing in this example. Now, if we do that, because we already know what is Q, therefore that is just going to be VQ. Note the difference between VQ and then the VP. The VP is that speed that the object is approaching the mirror, but the VQ is that speed that the image is approaching the mirror from the other side. Now, in that case, this is what you are going to do. Now, you take the time derivative of Q, and this is what you are going to do. And this is what you are going to have. Now, as a result, this is what you are going to have. Now, let me just, maybe because it can just be a little bit challenging for you, let me just do this so that you can see that this is just going to be like this here. Now, I'm just going to write that equation here because I have that equation here. I have this D. I have that D, the rate of dt is equals to fp, focal length multiplied by the object distance, and then here I have p minus f, and then that is the rate of change in q. Now, in this case, I'm just going to have d over dt here, and everything here is nothing else but everything here is what we call q. Right, when I have something like this, in mathematics, you remember your calculus class, I am allowed to multiply this by 1. Now, that 1 will just be d divided by dt, and then I multiply this by 1 by dp and dp and dp, and then fp divided by p minus f. I have done nothing to this equation. I've done nothing to this equation, but what I want to write this in terms of dp dt, and then here I want to write d over dp, and then I have fp minus pf. Now, in that case, I can take the derivative with respect to p for this equation, taking into account that dp, the rate, the dp, the rate of change in this object distance is nothing else but is what I'm going to call the VP. The VP. Now, in that case, when you take the time derivative here, this is I'm going to use the product rule. I'm going to call this the whole function here the f. In fact, I'm going to use the quotient rule. This one I'm going to call it g. Now, if you differentiate something like this, what are you going to have? You're going to have f prime, and then you leave g, you minus g prime, you leave f. All this must be divided by g squared. Now, if I do that to that equation, what I'm going to have here, now I'm starting to differentiate f, I'm leaving g. When I differentiate f, the f is this one. With respect to p, I'm just going to have there. What I'm going to have there, I'm just going to have, I differentiate this part. With respect to p, I'm just going to have f. I'm just going to have f, and then I leave g. F times g, p minus f. And then minus, I am leaving f. I'm leaving f, fp, and then I am differentiating g. When I differentiate g with respect to p, it's just going to be 1. Therefore, I can even write 1 there. But everything here must be g squared, and g squared is nothing else but is p minus f squared. Now, in that case, as you can see, this 1 here will cancel that 1. But that f multiplied by that 1 is just going to be what you call Vp, but then I will have f square Vp, and then I will have f square, because that will be f multiplied by f minus f square. I'm going to write minus here, and then f square divided by p minus f all square. So that's what you are having in that case. This is what you are having. So as a result, this is how you do that. This is how you solve that kind of problem. Now in that case, and you just put the values because you are given the values. This is what you are going to have in terms of the velocity of the image to the mirror. Right, now let us also do the following example 36.4. Now the image from the convex mirror. Now an automobile side view mirror as shown in the image on the passenger side, as shown in the photo of a truck located the distance of the truck, and then the mirror, the focal length. You are given the focal length. Find the position of the image from the truck. Now if you have to find that, we know what is Q. Q is just given by that, and then you are given all these things here. But what is very important here is the convex. The focal length of the convex mirror is minus. Therefore, that's why you have this minus and this minus here. Remember, the focal length for a convex mirror, it must be minus. That's why this minus sign here. Right. Please be very careful to use the sign convention, very careful. Otherwise, you are not going to get the right answer. So that's what you are going to have for your Q. Now find the lateral magnification of the image. Now the magnification is just given as positive. That means that the image is facing on the same direction as, but it is actually a visual image because it is actually a positive. Right, it is actually on the other side. Right, let me also introduce you to the image formed by the refraction. Now in this case, a ray making some angles with the principal axis diverges from a point, from the point object at O, and are refracted through the image point I. Now in this case, as you can see, this is the object distance to this side. Now in this case you have A here, this is N1. In this case you have N2. Now in that case you have the radius of the curvature, and here you are just going to have your image. Now if that is your image, therefore that distance from the surface there to there is what we call Q. Now rays originate from the object at point O in the medium with N is equals to N1. Now in this case, if N1 is less than N2, for instance, if you have a glass here and then you have air here, right? Now in that case, I'm just going to use the same thing, and then I plot this. I'm only taking one ray, though there are many rays, of course. I'm just taking one ray, and then I name this angle as alpha, and this angle here, because it is just going to be reflected back there. Now the normal is just going to be through the center of the curvature there, and then I name this angle here what you call the gamma. Now in that case, as you can see from this, I just have to consider the paraxial rays living at O. All such rays are refracted at the spherical surface and focus at an image point I. Now in that case, if I've named all these angles like this, the first thing that I'm seeing is that the theta 1 is just the exterior angle is just alpha plus beta, while the beta can be written in terms of q theta 2 and gamma. Now when you do that, and from the Snell's law, because we know what is the Snell's law is given by this. Now in this case, for a very small angle approximation, the sine of theta, for small angle approximation, I think you still remember that, for small angle approximation, the sine of theta is nothing else but is approximately equals to theta. Even the tangent of theta for small angle approximation is just the same as that. Even the cosine of theta for small angle approximation for the paraxial rays. Therefore, this is just going to be nothing else but this is just going to be this, the n1 theta 1 and is equal to n2 theta 2. But now, what is theta 1? Theta 1, the exterior angle of this triangle. Now theta 1 is just going to be alpha plus beta, right? Theta 1 is going to be alpha plus beta. Now from the exterior angle of a triangle, I can see that beta is just going to be theta 2 plus gamma, right? Why I'm doing this, you'll see now I can just plug. Whenever I see theta 1, I can plug whatever theta 1 is. Whenever I see theta 2, I can plug whatever theta 2 is, right? Now in that case, I can also take the tangent of alpha from this triangle. This is what you are going to have. Now I can also take the tangent of the beta, and I can also take the tangent of gamma. Why Why I'm doing that? Because I want to plug the alpha, I want to plug the gamma, and I also want to plug the beta, because I know them from this small angle approximation. Now, when you plug that to this equation, this is what you are going to have. And that equation here, in terms of the magnification therefore will just be given as negative n1 q, the distance of the image, and then the n1 multiplied by the distance of the object. Right. Now the side of the surface in which the light rays originate is defined as the front side. The other side is called the back side. Now real images are formed by a refraction in the back of the surface. Because of this, the sign convention of Q and R for a refracting surface are opposite those of refracting the surface. Now this is some of the sign convention in terms of the refracting surface, and this is the equation that you are going to have. Now let me also introduce you to the flat refracting surface. Now in terms of the flat refracting surface, now if the refracting surface is flat, then R is infinity. The radius is just infinity. As a result, this side is just going to be 0, because that number divided by infinity is just going to be just 0. Now in that case, then Q is just defined in terms of this equation, n2 divided by n1 times p. Now that will mean that a visual image is actually formed when n, say example water, and then you have air there. So this is a very good example of that. Now this is just going, that equation will just reduce to be given by that equation here. Right. Now let us also do the following quick quiz. In the figure, what happens to the image point if the image point I as the object point O moves towards the image hand surface of the material of index of refraction n1? Now it always remains between O and the surface, arriving at the surface just as O does, unless maybe if you can change the refractive index of one of this material. Right. Therefore, that will be the answer. Now, let us also do the following conceptual example, 36.6. A set of a coin is embedded in a spherical plastic paper weight having a radius of 3.0 centimeter. The index of refraction of the plastic is given. One coin is located 2 centimeter from the edge of the sphere. Find the position of the image of the coin. Now, in that case, we know what is the equation, the distance of the image, and then if you rearrange that equation, this is what you are going to have. Right now, in that case, this is what you are going to have, because you know the n1 is the n2, the n1 is that, the n2 is the a, that is why you see 1 there. But what is the radius? The radius of the curvature here, from the sign convention, of course, it must be minus, because it is on the other side, therefore it must be minus. Therefore the q, distance of the image, is just given by 1.7. You are just going to see that this to be somewhere. You will see this to be here. Right. Now let us also do the following example at 6.7. A small fish is swimming at the depth d below the surface as shown at this image. What is the apparent depth of the fish as viewed from the direct overhead? Now in that case, because this is the flat surface, we just have to use this that equation where r goes to infinity. Now the q is just given by this equation, therefore q is just given by that. But that p is nothing else, but that p is just d, because that is the distance of an object. Right. Now if the face is if your face is a distance d above the water surface, at what apparent distance above the surface does the fish sees your face? Now in that case, n1 and n2 will just interchange. Now if they interchange, therefore q will just be given by this equation here as negative 1.33d, and it is negative because it is on the other on the other side. Right. Now what if you look more carefully at the fish and measured its apparent height from its upper fin to its lower fin? It's the apparent height age of the fish different from the actual height. Now, in that case, when you solve that, the Q from the top, this is what we have received. This is what we have gotten. But the Q from the bottom is just going to be that plus that certain h height or h. Now, if you get the h prime will just be that the top minus minus the bottom. Now, that is just going to be 0.752 times h. Now, let me also introduce you to the lenses. Lenses are commonly used to form images by refraction. Now, lenses are used in optical instruments such as cameras, telescopes, as well as the microscope. Light passing through a lens experiences refraction at two surfaces. Now, the image formed by one refracting surface serves as the object for the second surface. Right. Now, in this case, the lens has an index of refraction n and two spherical surfaces with radii R1 and R2. The radii of the first one and the radii of the second one. R1 is the radius of the curvature for the first one, and the object is placed at point O. The object is placed at point O at the distance P1 in front of the first surface. That is Q1. Q1 is going to be equals to P2, because this will just serve as an image for the second one. Right. Good. Now, there is an image formed by a surface 1. Now, since the lens is surrounded by the air, N1 is equals to 1. Therefore, when you lose this lenses equation, this is what you are going to have. Now, N1 is 1. This is what you are going to have. And this is the equation that you are going to have, because N1 is just 1. Now, if the image due to surface 1 is visual, Q1 is negative, and it is positive if the image is real. It will just depend whether the image is visual or it's real, and the sign of the Q1 will therefore be determined by that fact. Now, for surface 2, N1 is equal to N and N2 is equal to 1. The light rays approaching surface 2 are in the lens and are refracted into air. Use P2 for the object distance for surface 2 and Q2 for the image distance. Now, in that case, this is what you are going to have. This is what you are going to have. That equation, it will just be like this for the surface 2, P2, Q2, and R2. And because here N2, because here N2 is 1, therefore that's why this equation is changing in this way compared to the previous one. Right. Now, in that case, if a visual image is formed from surface 1, then P2 is just nothing else but it's just minus Q1 plus T, where this T is nothing else but the thickness of your lens, the thickness of your lens. But for very thin lens, T can just be ignored. It can just be ignored because it's very thin. Things like thin films. Right. Now, T is thickness of the lens. If a real image is formed from the surface 1, then P2 is just given by that equation. P2 is nothing else but it's just the image from the lens number 1, right? Plus T, and Q is positive. As a result, that equation therefore can be written in terms of this equation, right? Now, a thin lens is one whose thickness is very small, as I've already said. Now, for a thin lens, the thickness T of the lens can just be neglected. In this case, P2 is nothing else but it's just equals to minus Q1, because the image for the image for the first lens is an object for the second lens. Therefore, that is why P2 is equals to negative Q1 if the image is visual. Now, then the subscript on P1 and Q2 can therefore be omitted. They can therefore be omitted. We can therefore write P and Q. We can therefore write P and Q. That is the focal length of the thin lens is the image distance that corresponds to an infinite object distance. This is the same as for a mirror. Now, the lens maker equation is therefore this equation given here. There's no need for you to put the subscript here because P is just that distance of an object, and then Q is that the final image, right? Because P2 was just equals to Q1, remember from the previous slides, and this can be written in terms of the focal length in terms of 1 over f, right? Now the relationship among the focal length, the object distance and the image distance is the same as for the mirrors. Now the notes for on the focal length and the focal point on the thin lenses, because light can travel either direction through a lens, both lenses. One focal point is for light passing in one direction through the lens, and the other one is for the other opposite direction. However, there is only one focal length. Each focal point is located the same distance from the lens. Now, for an example, this is what you are going to have for a focal length of a converging lenses. The parallel rays passes through the lens and converge at the point of the focal point here, and that distance there is what we call the focal length. Now, the parallel rays can come from the left, or from the right. Therefore, they will just converge to that point, respectively. Right. Now, the focal length of a diverging lens. Now, the focal length of a diverging lens, the parallel rays diverges after passing through the diverging lenses. Now, it focuses at that point after passing the diverging lens. Now, the point is the point where the rays appear to have originated. Now, as you can see, this is the point where it seems as if these rays originated from this point, whereas this rays did not originate from here. Those rays were just coming parallel, but they are being focused as if these rays are actually starting from that point. And the same will also happen if these are coming from the right. Now, in that case, determine the signs. For us to determine the sign convention for the thin lenses, the front or visual side. The front is the visual side, and the back is the real side. Now, P is positive and Q is negative. Now, P is negative for the back side, and Q is positive for the other side. This is the incident light, and then on the other side is the reflected light. Now, in terms of the table form, these are your sign convention for thin lenses. Now, in terms of the magnification is just the same as for the flat mirrors. Now, where M is positive, the image is upright and on the same side of the lens as the object. When M is negative, the image is inverted and the side of the lens is an opposite to the object. Now, thin lens shapes, there are different thin lens shape, bioconvex and convex concave, and then plano convex, and there are also more thin lens shapes for the convex. For example, you have a bioconcave, and then you also have the convex concave, and you have got the plano concave. Therefore, there are many different types of shapes. Now, in terms of the ray diagrams for the thin lenses or for converging lenses, the ray diagrams are convenient for locating the image formed by the thin lenses of the system of lenses. For the converging lenses, the following three rays are thrown. Now, the ray number one is thrown parallel to the principal axis and then passes through the focal point on the back side of the lens. Ray number two is thrown through the center of the lens and continues in a straight line. Ray number three is thrown through the focal point on the front of the lens, or as if it is coming from the focal point. If P is less than F, and the images from the lens parallel to the principal axis. Now, this is what I am talking about. This is the ray number one. It's thrown, moving parallel with this axis. When it is getting there, it is reflected through this focal point. Now, the second one is just going to via through the focal point, but when it's get there, it is getting refracted to this point there, and then the other one is just going to pass through the center. Now, where they meet, this is your image. Now, in this case, when the object is being placed in this side, the image is real. The image is real. The image is real. Remember, these are for lenses. The image is real. Please look at the sign convention. The image is real. The image is real because it's at the back side. Now the image is inverted and the image is on the back side of the lens, right? Because for lenses, the sign convention is totally different compared to the previous one that we have done. Now, if P is less than that, this is what you are going to have. If P is less than F, if the object is placed there, now the first ray is just going to go there and then reflected back to that focal point. Now the other one is just going to pass through the center, and then you do the dotted line to be going there, and the other one is just going to be passing through parallel, and then you can just construct those lines. And then in that case, the image is visual. The image is visual, and then it is upright. The image is larger than the object, and the image is on the front side of the lens. Please make sure that you understand the sign convention for the lenses. Now, rays for thin lenses, for the diverging lenses, I'm just going to apply the same rays in this case. Now, in that case, the ray number one, it goes like that, and then because this is the diverging lens, and then it's going that way, and then it's you draw these lines going to the this focal point there, and then the other one, for number two, is just going to go to that, and then when it is there, it's just going there. It's the one that is going to pass through that focal length for number two, and the last one pass through the center. Now the image is just there. Now the image is visual. The image is visual because it's on that side of the lens, and the image is upright. The image is smaller, and the image is on the front side of the lens. Please make sure that you look at the table. Right, now let us just do the following quick quiz. What is the focal length of the plane of a pane of window glass? It must be infinity. You remember, it must just be infinity. Remember that case, that R is just actually infinity for the plane surfaces. Right. Now let us also do the following conceptual example. A converging lens has a focal length. You are given the focal length, and object is placed 30 centimeter for a lens. Construct a ray diagram for find the image and describe the image. Now in that case, this is what you are going to have. The first one is just going to go like that, and then it's getting reflected through that focal point. The second one is going through focal point, and when it's there, it's refracted to that point. The other one is just going to go through the center, and the image is just going to be here. Now let us just do the calculation now. The Q is just going to be given by this. We know all the focal lengths, and therefore this is what is going to be in terms of the Q. Q is just going to be 15. It's just going to be 15. Now the magnification is just going to be given by this minus Q, the ratio of Q divided by P, and now if you plug those values, because you know what is Q, you know what is P, therefore it's just going to be minus. Therefore this minus is actually telling us that the image is inverted, it's upside down, it's actually upside down. Right, now the part B is saying that we have to locate it for 5 centimeter, if it is now 5 centimeter. Now if it is now 5 centimeter, you can also show with the ray diagrams applying the rules, but in that case Q is just going to be minus 10. It's just going to be on the other side, and the magnification is just going to be positive 2. It means that the magnification is positive, the object is actually pointing upwards. Right, so but the object now in this case, the image is higher than the object. Right. Now, what if the object moves right up to the lens surface so that P goes to 0? Where is the image? Now, in that case, if P goes to 0, this is what we are going to have. Q is just going to be equals to that. Now, the diverging lens has a focal length. I just want to also do this example for the diverging lens. Now, you are given the focal length, and then the object distance, and then construct a ray diagram and an image distance and describe the image. Now in that case, you just do the ray diagram. The first one will go like that, and then reflect it, and then you draw the dotted line through the focal point, and the second one is just going to go to the center, and then when it gets there, it's just going to be refracted in this way, and then you draw the dotted line for that. And now in that case, this is what is going to through that focal point, and the other one just passing through the center. Well, or where all these lines meet, this is where is going to be your image. Now in that case, we can also be using the lens equation to actually do that. But what I want you to see is that the focal length of this diverging lens is negative. That's why this minus sign there. Right, in that case, the Q is just going to be minus 6, and then the magnification is just going to be positive. It will mean that the object and the image are orientated, the orientations are pointing on the same orientation. Right. Now also here, I also want to show you that because this minus is from the equation, but f is minus for the diverging lens, therefore that will be minus multiplied by minus, that's going to be positive. Right. Now for part B, an object is placed at 5 centimeter. Now if the object is placed at 5 centimeter, you must always remember that this focal length is minus, and then it's always going to be minus. Now in that case, you have to minus the other one, therefore you can just see that the focal length is actually 10 there, but it's still minus, therefore that Q is just going to be given as 3.33 centimeter. Right, the magnification in that case is just going to be given by 0.667. Right. Now the combination of thin lenses, the image formed by the first is located as though the second lens were not present. Then a ray diagram is drawn for a second lens. The image of the first lens is treated as an object for the second lens. The image formed by the second lens is the final image of the system. Now if the image formed by the first lens lies on the back side of the second lens, then the image is treated as the visual object for the second lens. P will be negative. Now the same procedure can be extended to a system of 3 or more. The overall magnification is the product of the magnification of the separate lenses. Now in this case, we just have to consider a case of two lenses in contact with each other. The lens have a focal length f1 and f2. Now for the first lens, this is what you are going to have. This is an object, this is an image for the first lens. Now since lenses are in contact, P2 is just equals to minus Q1 as we have done. Now in that case, for the second lens, this is P2, but instead of writing P2, I will just write Q1. So this is what we are going to have. Now for the total focal length is just the combination of the two. Now two thin lenses in contact with each other are equivalent to a single thin lens having a focal length given by the above equation as I've just explained now. Now in that case, I want us to do the following conceptual example, that is 6.10. Two thin converging lenses of focal length f1 is given as 10 and f2 is given as 2, are separated by a distance d centimeter as illustrated in the figure. An object is placed 30 centimeter to the left of the lens 1. Find the position of the magnification of the final image. Now in that case, this is what you are going to have. You know what is Q1. You plug the values, and this is going to be plus 15. Now that is the image 1 is 15. Is 15. Is 15. The image through the lens number 1. Now in terms of the magnification is therefore is telling us that this image is inverted, and we can also use the ray diagrams to actually show that this image is inverted because the magnification is negative. Now in that case, that image 1 is going to be an object for the lens number 2. Now when you do that and taking into account this distance from there to there, 15 and 20, taking into account that, therefore for Q2, this is what you are going to have. 20 minus 15 is going to be 5 for P2. Now as a result, Q2 is just going to be given by this. Now the magnification therefore is just given as positive 1.33. Therefore the total magnification is the product of the both magnification of these lenses. Therefore the total magnification is therefore minus 0.667. What does that mean? It means that the object is inverted, is actually facing on the opposite side. Right. Now let me get into the last section of this chapter. It was a very long chapter, by the way. A simple magnifier consists of a single converging lens. This device is used to increase the apparent size of an object. The size of an image formed on the retina depends on the angle suspended by the eye. For example, the angle on your retina. Right. Now in this case, the size of a magnified image. For an example, say you don't have a magnifier here, and then things are just normal. This is what you are going to have. But the moment you have a lens, in that case, that height, it goes big. When an object is placed at the near point, the angle suspended is a maximum. The near point is about 25 centimeter. This is just 25 centimeter here. Now, when the object is placed near the focal point of the converging lens, the lens forms a visual and upright and enlarge the image. The moment you put the lens, the image is enlarged. Therefore, in that case, let us just look at the angular magnification. The angular magnification is nothing else, but it's just given as that the angle with lens and divided by the angle without a lens. Now, in that case, the angular magnification is at the maximum when the image formed by the lens is at the near point of the eye, which means that Q is just minus 27 centimeter, and the maximum magnification is just given, can be calculated from just this equation. In fact, it can also be shown that the maximum magnification will be given by this equation. Good people, now let us just try to actually show that. Now, when you have to show that the magnification is just given by this, now in that case, you can have the P in terms of this equation. This is what you are going to have in terms of the P. In terms of the P, this is what you are going to have if you rearrange this equation. This is your P. Now, the tangent of theta naught can be given by this equation, and the tangent of theta when there's a lens there, this is what you are going to have. But this magnification is that ratio of that to that. Now, which means is the ratio of this to that. Now, if you do that, if you want to put the ratio of that to that, you will end up with this, taking into account what is your P. Your P is just given by that equation there. Therefore, this has actually shown that maximum magnification can be given by 1 plus 25 centimeter divided by f, if the distance from the eye to the object was 25. If it was 30, therefore you will have 30. If it was 50 centimeter, therefore you will have 50 centimeter there. Good. Now, the eye is most relaxed when the image is at infinity, although the eye can focus on an object anywhere between the near point and infinity. For the image formed by a magnifying glass to appear at the infinity, the object has to be at the focal point of the lens. The angular magnification is therefore given by this, which is nothing else but the minimum angular magnification is just given by this equation. So good people, with this I would like to pause here, and these are your tutorial problems. And believe it or not, good people, this is the very simplest chapter that we will ever do at the university level, but it is just a very long chapter. So keep well and goodbye.